Today, the photoelectric effect actually has numerous applications in technology that we have every day. If you think about some devices as simple as the digital camera, this makes use of the photoelectric effect. Long gone are the days when we rely on film in our cameras, using silver bromide film. Instead, we have cameras today with so-called charge-coupled devices that convert photons of light into small currents that are detected in a circuit. The CCD sits behind the lens, and the light is focused onto it. And each CCD is generally divided into small pixels. So this small silicon wafer is divided into a grid of small pixels, often millions of pixels at a time. Each pixel operates via the photoelectric effect, where a photon comes in and hits it and creates a small charge released. The idea of photovoltaic cells derived from the same way. Photovoltaic cells, you take photons from the sun and convert it into a current. This is stored either as energy in a battery or delivered to systems for use by end users. But all of that is just making use of the photoelectric effect. There's also another instrument called the photomultiplier tube, which would make use of the photoelectric effect to detect faint amounts of light. A photomultiplier tube is essentially an evacuated small cylinder where a photon comes in through a window, shown here on the left-hand side, and hits a small piece of metal, which is at a voltage. When the photon hits the window, it is sometimes coated with a material that has a very low work function associated with it. When the photon hits that material, that photocathode is called, an electron is ejected and is accelerated downward toward this U-shaped piece of metal. And when that electron hits that metal, it makes the metal eject another electron, and it's accelerated over to another small piece of metal over here, which is held at an even more positive voltage. And now that one electron in comes and hits that piece of metal and makes two electrons, the original plus one more that's ejected out of the metal. Now those two electrons are accelerated toward yet another piece of metal held at an even higher voltage, and two electrons become four, and that's accelerated to yet a fourth piece of metal, and the four electrons become now 8, and 8 becomes 16, and so on. And at the end of several of these so-called diodes, these U-shaped pieces of metal held at higher and higher voltages, one has a current that's very appreciable, perhaps as large as microamps. So something on the order of 1,000 volts difference between the first and the last diode is sufficient to create a current that's detectable from one single photon that came in and hit that window at the front end of the photomultiplier tube. So the photomultiplier is a very great way of detecting faint amounts of light, single photons. There are all kinds of shapes and sizes for photomultiplier tubes. Most of them look like about the size of a soda can. So it looks like this. The photon would come in at the front end here, and you notice that window has a coating on the inside, so it looks a little dark. That's the material that has a low work function and ejects an electron. And now that electron is accelerated down the diode chain throughout the volume of this tube. This particular tube has been exposed, so you can see the glass on the side. You wouldn't want that in an ordinary photomultiplier tube, otherwise light would be coming in the side. This would all be wrapped, so the only way for light to get inside is through that front window. The pins on the back are to make this photomultiplier tube connect up to a high voltage source. Some photomultiplier tubes are a little bit bigger. Some are quite a bit smaller, in fact, and fit on the tip of your finger. And in many cases, people are making large camera arrays out of multiple photomultiplier tubes with lots of little pixels. This is a camera array for a space-based telescope. Some photomultiplier tubes are used in particle physics all the time, and in use of detection of neutrinos. One of the more famous experiments in particle physics is called the Super Kamiokande experiment in Japan. It actually consists of a giant cylinder, a cylindrical vat of water. It weighs about 50,000 tons of water, and its height is about 200 feet in height. So this distance here is about 200 feet. It's truly massive. You can walk around inside of it or swim around inside of it because it's filled with water. This is deep underground in a mine. And the idea is that an invisible neutrino comes in and penetrates the Earth very easily, but once in a while will interact in the water. And when it does, it creates a shower of other relativistic particles. These particles cause a shock wave of light, and the light propagates out through the semi-transparent water until it hits the walls of this giant vessel. The walls have been lined with thousands of photomultiplier tubes all across the walls, and you detect the flash of light with those photomultiplier tubes. Just to give you a sense of how big this thing is, here are some pictures. So the water is being filled inside of this vessel, and in a little pontoon boat are some scientists, probably graduate students, cleaning some of the photomultiplier tubes on the walls. Notice these are particularly large phototubes. They're about 20 inches in diameter. Here's a fisheye lens looking up at the top of the tank. Again, there's a little bit of water at the bottom, and folks are riding in a pontoon boat, and you're looking up high, 200 feet up in the air toward the top of this giant vessel, and you can see photomultiplier tubes all around it.